All right, so in this video, we're going to take a look at a couple more volume setups, and then we'll also take a look at how to reverse the order of integration given a certain problem. Now, what we're doing here is really nothing different. They're presenting it slightly different, but what we're doing is the same thing. So we're going to find the volume under this surface and above this region. The region they're giving us is the triangle with the following vertices. And so when we get this set up to start, really the first thing that I would do is I would just throw in this guy right here. Right off the bat, you know that that's going to sit right there. Just put it in place and let it sit. It's really not going to come into play much more in this particular problem. You'll notice very quickly, if you haven't done so already, 90% of our time is spent deciding what's going on here and what's going on here. And that's always in R2 for these types of problems, and so that makes it a little bit easier to manage. Now, before deciding if we want to go horizontal or vertical, I would certainly want to take a look at the region a little more closely. So this region that they've given us is going to be in the XY plane. Remember, the z-axis is coming out at us. The surface is doing something above, and with this triangle that I'm going to sketch in here, that's where those rectangular prisms are coming out and up, giving us a volume to compute. So these points would be, let's see here, -3, -4 we'll put down here, -3, +4, -3, +4 we'll put right there, and then 5, 0 would be somewhere over here. So if I sketch this out, here's going to be my region. Now, what our first goal here is to decide, do we want to go dy dx? Well, if we go horizontally, let's say, I think that's a bad decision because my right and left there would be different than my right and left there. So I don't think horizontally is the way to go. However, if I go vertically and I scan this thing from here all the way over, my top and bottom are the same. So I think vertical is the way to go here. Vertical means that this thing's scanning from left to right, which means our constants are going to come from the x values. If our constants, which will always end with constants, are going to come from our x values, this has to be a dy dx problem. Okay? And so we can see these constants actually from the picture without having to do a whole lot of work. We can see that we're going to need to start here at -3, and it's going to move all the way over to 5. So -3 to 5 on the outside, pretty straightforward. Now, to decide the top and the bottom, well, these are just lines, and you have 2 points, another line there, and you have 2 points, so we're just going to use those points to come up with the equations of those lines. Now, we do want to remember this is going to be a y equals, so fortunately it's going to be a very standard process in coming up with those equations. I'm not going to run through the entire process. It's one of the perks of teaching Calc 3 is that my audience knows how to find the equation of a line given 2 points. So this is going to be y equals -1/2 x plus 5/2, and this guy here is going to be y equals +1/2 x minus 5/2. And so my top would go right here, my bottom would go right here. So I'm going to have y equals -1/2 x plus 5/2 and y equals 1/2 x plus 5/2 down there. And so this would be our setup. And that's all we're going to do on this one and the next one as well. We're just going to get these set up. Now that we've gone through how to do them, I think the setups are really going to be what the new stuff it entails. So yeah, again, once you decide this guy right here, and usually based upon the picture, then it's just a matter of getting the bounds filled in. All right, so in this example, we're going to be finding the volume inside of this guy here and above this guy here. So now we're going to have to go back to our quadric surfaces discussion from much earlier in the course. But fortunately, these aren't too bad. This one's just going to be a sphere centered at 0, 0, 0, radius √2. And this one's going to be your paraboloid that opens up. So let me sketch this picture out. I'll go ahead and just put my XYZ plane to start. And we've got our sphere looks something like this. And then that paraboloid would do this. So we're inside the sphere and above, or I guess inside in this case, the paraboloid. So this is where we are in R3. So this stuff right here, a bit on a different color. There we go. So that's what we're looking into, finding the volume of. Now, when I get this thing set up, there's a couple things that jump out at us right off the bat. The first is something back from Calc 1. We're no longer coming up strictly from the XY plane like we have in every other example. We're actually going to have now a top and a bottom that are different. So the top would be this guy and the bottom would be this guy. So just like in Calc 1, now sitting in here, you're going to have a top minus bottom. So our top part would need to be this part right here, the sphere, and our bottom part would be this. Now remember, these have to be z equals, and so for this guy, when I solve for z, I'm going to have z equals the square root of 2 minus x squared minus y squared. And since this is the top half of the sphere, I'm going to take just the top part of the positive part of that. So that's going to be the square root of 2 minus x squared minus y squared, and then minus the bottom of x squared plus y squared. So again, this is a little bit different now, but it takes us back to our Calc 1 concepts of this whole big minus this little, top minus the bottom. Now, our next step is to decide, do we want to go dy dx or dx dy, and then focus on the bounds. But this one too is a little bit more challenging, because what we're needing to drop into R2 is going to depend on where we intersect right here and right here. So we need to find the z value where these things intersect. Once we find the z value where these things intersect, it's going to be pretty clear that I'm going to have a circle then in R2. But that z value is going to be very important where these intersect. That way I can then drop down that projection into R2. Okay? So to figure out that z value, what I'm going to do is I'm going to move over to this first one and say that x squared plus y squared equals 2 minus z squared. 2 minus z squared, there we go. And then I also know that x squared plus y squared is equal to z. So I'm going to take z and set it equal to this. So z equals 2 minus z squared. Now if I solve this for z, that's going to give me where we intersect. So solving this, we get a z squared plus z minus 2 equals 0, which factors into z plus 2, z minus 1. And so we get a z equals negative 2 and a z equals a positive 1. The negative 2 clearly doesn't apply here, and so z equals 1 is what we want. If z equals 1, then from both of these, and again, that's important to acknowledge, from both of these, if I let my z equal 1, I'm simply going to get an x squared plus y squared equals 1, and that's going to be now the region that I need to study for the dy dx and the bounds here. Okay, so it's important to take the intersection of these at z to drop down and get our projection then into R2. So for one like this, it doesn't really matter which way we go. If it doesn't matter, I generally will go dy dx because it wipes out the y first. It allows us to solve for y with our functions, which is a little more traditional, I suppose, but beyond that, it really doesn't matter to me. Some of it's going to boil down to how we integrate this, but I'm going to mention that at the end of the problem anyway. So let's say we go dy dx. Well then, if we go dy dx, that means we're going vertically. The top part here would be y equals the positive square root of 1 minus x squared. And this then would be the bottom, y equals negative square root 1 minus x squared. So here we have square root 1 minus x squared, negative square root 1 minus x squared. And then this would move or scan from negative 1 over to 1. So there would be our negative 1 over to 1. So there's our setup for this particular problem. A little more in depth because of how the problem was presented, but beyond that, right here, this part was all kind of the same. Now, I do want to mention, I said it briefly that a lot of times the order of this depends on obviously what can happen here, but additionally what's going to be easiest to integrate. And this one's very, very difficult to integrate in terms of x's and y's. Fortunately, we're going to have different coordinate systems that are going to come into play later in this chapter. So I'm not going to really push it a whole lot right now, but do expect, and you can probably see some things available to us with x's and y's. Do expect these to be made a little easier, hopefully, by using these other coordinate systems down the road. All right, so the last thing we need to talk about here is how to reverse the order of integration. And this is an incredibly useful skill for many problems. And so what it means is that we're given a dy dx, and we're going to come up with an equivalent double integral, but instead of dy dx, dx dy. So what I would do first, and many times this is how it's presented to us, just like this, but what I recommend doing is actually taking these bounds and rewriting them as equations. So for example, this e right here, this we know that by how the order works, this would be an x equals e, x equals e, x equals 1, and these would be y equals from this guy. So we would have y equals the natural log of x, y equals 0, x equals e, and x equals 1. Then I would go ahead and draw a picture of that region. So our region then would look something like this, where we have our y equals the natural log of x right here. We would have y equals 0. Well, y equals 0 would be this guy. We would have x equals 1. X equals 1 is right there. I'll mark that here. There's x equals 1. And then here is x equals e sitting somewhere over here. So this looks to be the region now that we need to study. And for us, they went ahead and started us dy dx. Dy dx was vertical, so their setup looks like this. Okay? But that's not the setup we want. They want us to switch it up, and so now our setup's going to look this way. So we'll have our double integral f of xy dx dy, and we want these to be x equals, and we want these to be y equals. So in terms of the y's, this one's pretty easy, I think. If we take our lower right here and go all the way up to the top, the lower is going to be 0. And then if we come all the way up to the top, that's going to be this guy right here. And that's going to be where this vertical line and this curve intersect. So if I take e and plug it into the natural log, I'm going to get this value to be 1. So that's going to go from 0 to 1. Now, in terms of the x's, this is going to be the right, and this is going to be the left. So the right's pretty easy. That's x equals e. So x equals e would go right there. And then this guy here, whoops, this guy here, we would actually need to solve for x. So to solve that for x, this guy right here, so to solve that for x, that's just going to say that x equals e to the y. So when I take that now, and I plug that in, now my setup is different in the order of integration, but it will still give you the exact same answer. Again, very important because many times the actual integration process can be difficult, but if you have the option of interchanging, it might make things a whole lot easier for you. So this is a really, really helpful skill to have.